Hi everyone, so in this video we're going to talk about the energy equation, and before going into the energy equation I like to start with the Bernoulli equation because the energy equation looks similar to the Bernoulli equation but with some added little tidbits. So this is our Bernoulli equation where we have the summation of our pressure head plus our elevation head plus our velocity head, okay? Now, according to this equation, this means that the pressure head and the elevation head and the velocity head are constant along the streamline. So in this diagram here, we have 3 points. We have 1, 2, and 3. And what this is saying is that the total energy, so our elevation head, our piezometric head or our pressure head, and our velocity head, when you add these up, you end up with some energy, which is this line here. And what this line is showing you is that that energy is conserved, it is constant as you're moving across the system. So energy at 1 is equal to energy at 2, which is equal to the energy at 3. Okay, so that is what the Bernoulli equation is telling us. Okay, in order to use the Bernoulli equation, we need to have steady flow, we need to have inviscid flow, so we have no friction effects, and we have to have our fluid that's incompressible. That one is really important because that means that the specific weight, okay, is constant. Well, actually, it means that your density, but your specific weight is just density multiplied by gravity. But if you have incompressible flow, then your density is constant as you're moving from one end to the other. And that's really important when applying the Bernoulli equation, okay? The energy equation, okay? The energy equation considers a few changes in the system. So first of all, you might have a system that experiences some energy losses, and those losses can be from friction or the pipe configuration. And so we would typically just refer them as what's called HL, as our energy loss, okay? The system can also have a pump, okay? If the system has a pump, then we have energy added, okay, to the system. And so we would denote that as HP, our energy added to the system, the head due to the pump. We could also have a system that has something called a turbine. And what turbines do is they actually use the difference in potential and kinetic energy, and they store the energy in, a local battery. But that energy is removed from the system and taken elsewhere. And so we usually represent this loss as HT, which is our head taken or lost from the system due to the turbine, okay? Now, we must consider the mechanical energy of the system now with the energy equation. So mechanical energy must be in balance within our system. The mechanical energy in is equal to the mechanical energy out plus any losses, okay? So it is essentially the Bernoulli equation plus any mechanical gains minus any mechanical losses. So again, pumps, so this is going to change the mechanical energy of the system. A pump is going to add mechanical energy into our system because it moves water from a lower elevation or a lower potential energy to a higher elevation or a higher potential energy. So think about it this way, right? In the olden days, they would have some kind of well, right? And this well would basically take water from really deep below the surface, and what they would do is they would construct a pump, okay, maybe like a hand crank sometimes, and what it would do is it would pump, it would take that water that's again below the surface and cause it to move from a low elevation to a high elevation. So that pump is adding mechanical energy into the system, okay? Now, the opposite happens with a turbine. So with a turbine, we're removing mechanical energy from the system. So what we're essentially doing is we're moving water from a higher elevation or a higher potential energy to a lower elevation at a lower potential energy, and we're storing that energy externally. So that's what I was saying with that turbine takes that energy and moves it somewhere else, similar to like a battery. Okay, so an example of something like this would be if you have a dam. Okay, so you have on the back end of the dam with a reservoir side, you would have very deep water, you would have high potential energy. Okay, in the dam, you would have some kind of turbine that would take that energy, store it into a battery, and then release water on the other side, where now we have a lower potential energy. Okay, we have a lower potential energy as that water is released. Okay, the last change to our mechanical energy is just mechanical loss, which is removal of mechanical energy from the system due to the piping network. And this can be because of very rough old pipes causing a lot of friction, or it can be from a lot of bends, turns, filters, things like that that do cause losses along the way. So now in the energy equation, we have to consider our mechanical energies. So our equation then becomes this. So I can see some pieces actually knocked off when I transferred to this program. So let me just fix this really quick. All right, now we're back in order. Okay, so everything in blue, okay, that is the head carried into the control volume by flow. So this part in the blue is very similar to the Bernoulli equation, right? I'm gonna highlight these alphas and I'm gonna explain them in the next slide, but very similar to the Bernoulli equation. Same thing in here in the red, right? This part here looks like the Bernoulli equation, and this part here also looks like the Bernoulli equation. But I want to make sure you see this equal sign. So everything on the left-hand side, everything on the left-hand side of the equal sign is considered energy into the system. So in addition to our elevation head, our pressure head, and our velocity head, we also have this head added by pumps. So that's again that energy into the system. Pumps add energy into the system so that we can have that extra elevation gain when needed. On the right-hand side of the equation, right, we have all of our energy leaving our system. So we have our elevation head out, our pressure head out, our velocity head out, right? We have these out. And then in addition, we have our head loss due to any viscous effects or any friction. So that's accounted for here in this head loss term. And you have additional losses if we have a turbine here. So again, everything on the left-hand side of the equation is energy into the system. Everything on the right-hand side of the equation is energy out of the system. You cannot mix up the location of the turbine parameter, the loss parameter, or the pump parameter. If you put it on the wrong side of the equation, you're in big trouble. Okay. Another thing to note is that this equation is set up in the direction of flow. So this equation is set up going from 1 to 2. Now, I want to make sure you understand what this means here. So if you have something like this, where you have a configuration, let's say you're going from here to here. You're going from 1 to 2. And let's say you have a pump, okay? So you're going from 1 to 2. Now, if you have a pump, okay, that means you're taking fluid, taking water from a lower elevation, so this would be my lower elevation, to my higher elevation here. That means the direction of flow must be going this way, okay? It must be going from low elevation to high elevation. So when you set up your equation, it's going to be like this. Now, we know our losses, we know that we don't have a turbine. We don't know if our losses are going to be negligible. So we can go ahead and make sure we include that in our equation here, okay? Now, what if we had a configuration that looked like this? What if we were going here, down, and this time we're passing through a turbine. So we're going from 1 to 2, okay? Now, because we have a turbine, and the purpose of the turbine is to take that energy from the system, so you're going from high potential energy to low potential energy. So that means that your elevation must be lower at 2. So your direction of flow is going to go like this. Okay, so then your setup is going to look like this, where this is 0. We have no pump in the system. We're not sure if we have losses, so we have to consider it, okay? And we have our turbine, okay? It doesn't matter if the turbine sees, so this is a question that I sometimes get from students is, well, the fluid is interacting on the with point 1 sooner than point 2, so doesn't it make sense to write the equation kind of as you see it? So you're hitting the turbine first, and then you hit you're hitting the turbine from the one side, right, first. So wouldn't you write it this way? No, never write it that way, okay? The turbine is always going to be on the right-hand side of the equation, always. The pump is always going to be on the left-hand side of the equation, always. And we always write our equations in direction of flow. So here's another curveball. Okay, so what if I change things a bit and I said we were going something like this. Let's say, okay, what if I'm change the numbers a little bit, okay, and I said we're going from 2 to 1 now, okay? It doesn't matter if we're going from 1 to 2 or 2 to 1, okay? As long as it follows the rules, right? For turbine, You always go from high elevation to low elevation. Always. Okay. You set up your equation in direction of flow. Okay. You set up your equation in direction of flow. So that means your equation is going to go from 2 to 1. We have no pump. Get rid of that. We might have losses, and we have our turbine. Okay. The ones and twos, don't get so bogged down by the ones and twos. What matters is moving in direction of flow. That is the only thing that matters. Okay. You set up your system moving in direction of flow. Okay. And you make sure that that pump, if it exists, is on the left side of the equation, again, because this is everything. This is all your energy in to your system. And on the right-hand side is all energy exiting the system. Okay, that's it. As long as you can get your setup just like this, you're in great shape. Okay, now I'm going to explain that alpha term. So that alpha term is called the kinetic energy coefficient, and it is essentially kind of like a fudge factor in the that occurred during the derivation of the energy equation. So for turbulent flow, the velocity is pretty constant going across the section for fully developed turbulent flow. So the alpha is approximately 1. Okay, again, for turbulent flow. For laminar flow, so this is when we have very slow moving flow, very low velocities. The velocity profile is approximately parabolic, and the integration gives you alpha equal to about 2. A lot of the times heading into the Bernoulli equation, we don't know the velocity. That's something that we generally have to find using the conservation of mass. If the kinetic energy coefficient is not given, okay, you can assume that we have turbulent conditions. So you can assume that the alpha parameter is 1, which is unity, and you can essentially just kind of get it out of the equation. As we head into chapter 8, okay, your alpha term is not going to be equal to 1, and there are specific kinetic energy coefficients that are used in those problems. So just as a heads up. Okay, so mechanical power. So in these problems, you are going to have to calculate what's called the shaft power. And so that W dot, okay, that is our shaft power and is the product of the shaft torque and the rotational speed of the shaft. So W dot shaft is torque multiplied by the rotational speed, okay? You're going to see this shaft power for both, actually for your losses, for your turbines, and for your pumps. So the first parameter, so we're just focusing on this head due to the pump. So let's say you're going forward and you're solving for the head added into you're solving for the head added into the system due to the pump. Great, wonderful. But that might not be the question. The question might be, well, what is the shaft power of the pump? Okay, so what this question is actually asking for is this W dot pump. Okay, now to solve for that W dot pump, you would use this equation where H pump is equal to the shaft power of the pump. So let's focus on this part. The shaft power of the pump divided by M dot, which is our mass flow rate. So M dot is mass flow rate, which is density multiplied by Q, or this M dot G is density multiplied by Q multiplied by G, which density multiplied by G is just gamma Q, okay? So that is going to be the pump due to the head. But this equation is essentially assuming that you have a perfect efficiency. As pumps age, they become less efficient, and the energy added to the system begins to degrade. Um, if that happens, then you have to add this energy efficiency term. So that pump efficiency here is essentially added when you have less than 100% efficiency. Okay, as we're doing problems, sometimes there's no information given about the efficiency of the pump. If there's no information given about the pump efficiency, then you can assume that the efficiency is 100%. If it says anything about solving for it, or it says something about the shaft power, the expected or the observed is different, then you have to solve for that efficiency parameter, okay? So that is the extra equation for the pump head. There is a similar equation here shown for the head due to the turbine, okay, where again you have your shaft power from the turbine divided by your mass flow rate multiplied by gravity. And this also, if you have efficiency less than 100%, you have to add this term, this efficiency parameter. I want you to notice that I made these notes on the side for you. So for a pump, okay, the efficiency parameter is in the numerator, but for a turbine, the efficiency parameter is in the denominator. So make sure that you make a note of that. And also note that, again, that m dot g could also be written as gamma q, okay? Which leads me to the last equation, which is the head loss term. So this head loss is equal to w dot loss divided by m dot g, which is w dot loss divided by gamma q. They're equivalent. Use whatever's given to solve for this. You would notice that there's no efficiency term. Of course, you either have some loss or you don't. It's not a function of any kind of degradation, such as, you know, with the turbine and with the pump, you know, over time their efficiency changes. So just keep that in mind. There are problems that do ask for the shaft power due to the loss. Sorry, this is turbine. Due to loss. Okay? All right. One thing that I have on the bottom here is this conversion term. So make sure that you have this handy. So very commonly when we're using BG units, we wouldn't calculate our shaft power in pound foot per second or anything like that. We would use horsepower. And you know, if you've bought a vehicle, you might have seen something like that on TV. It's like has X amount of horsepower, right? That is the shaft power that we're talking about. So this is just kind of like a sample calculation. So you'd have some head, which is equal to W dot divided by M dot multiplied by gravity. And so this is an example of plugging in the units in BG. So that W dot does tend to be given in horsepowers. One thing I want you to note that I know this is really unfortunate, but you should be very careful that HP, if that's given, and that's talking about power, okay, that, right, commonly used in a unit of power. This is not the head due to some pump. Sometimes students misinterpret that when they're reading the problem statement where it says, the shaft added 10 horsepowers of energy to the system. Okay, great. That's the shaft power from the pump. That is not HP. Okay, that's not the head added to the pump. The head added to the pump in these units will be in feet. Okay, W dot is going to be in horsepower. So that these are the units for W dot. Okay, so to convert, again, horsepowers to convert pound force foot per second into horsepowers, you would just multiply by that 550. So make sure you have that somewhere, that's a really important conversion. This is just showing kind of everything together where you have your energy due to the flow. So this is from similar to the Bernoulli equation. At 1, you have energy, that's the energy into the system. You have energy exiting due to the flow at 2. But then you also have this extra added into the energy into the system, which is due to pumps. And you have extra energy leaving due to the turbines and due to our losses. So previously you only had, again, these 2 things to account for, but now you have these additional things to account for. So you have pumps and turbines and losses. Okay, so this is just showing the comparison between the energy equation and our Bernoulli equation. Okay, again, major differences being this coefficient here, our head due to the pump, our head due to the turbine, and our losses. So those are major differences that we must consider in the energy equation versus the Bernoulli equation. The Bernoulli equation is very simple. Again, when you have inviscid flow, that's a super simple simplification. With the energy equation, we include everything. Okay, so don't be fooled. The energy equation does look a lot like the Bernoulli equation. However, there are major differences. The Bernoulli equation was derived by applying Newton's second law to a particle and then integrating along a streamline. The energy equation is derived using first law of thermodynamics and the Reynolds transport theorem. So this derivation is in our book. And I also have a supplemental video that I suggested that you watch, again, to supplement this lecture. The Bernoulli equation only has mechanical energy, whereas the energy equation has both mechanical and thermal energy. So it considers both in that derivation. Most importantly, even though they look the same, the energy equation is a control volume equation and relates inflow and outflow. The Bernoulli equation is not a control volume equation. It equates the mechanical energy of 2 points of a flow in a flow. The energy equation applies to steady, viscous, incompressible flow in a pipe with energy added or lost. Versus the Bernoulli equation, which just considers steady, inviscid, incompressible flow. Again, no losses or additions. So whatever energy you put in Bernoulli equation, you get out, but that's definitely not the case with the energy equation.